Have you ever wondered what truly powers the digital world around us? I mean, we interact with technology every single day, right from the moment we check our phones in the morning.
Yeah.
To browsing websites, streaming movies, or even when those massive corporate servers hum quietly in some distant data center.
Mm-hmm.
But what if you could actually peer behind the curtain, see what's running on nearly every server, every supercomputer, even the smartphone you're holding right now?
Right.
What if you could understand the operating system that powers so much of our modern life, often without you even realizing it's even there?
It's a fascinating question, really. And what we're talking about, it isn't just a piece of software, not at all.
No.
It's more like a profound philosophy, a really vibrant community, and honestly, an enduring testament to the sheer power of open source development.
Okay.
Our discussion today, I think, will connect these, seemingly abstract ideas to the bigger picture of how technology evolves and maybe more crucially, how it empowers or sometimes, disempowers its users.
Welcome to the Deep Dive, presented by Knowledge Flow. This is where we take a stack of information and distill it down into the crucial insights you need to be truly well-informed.
Mm-hmm.
Today, we're embarking on a deep dive into Linux. We're not just looking at what it is, but its, kind of unexpected origins, the unique philosophy that drives it, how it's fundamentally built.
Yeah, the nuts and bolts.
Exactly. And the powerful, frankly pervasive ways it's used every single day, all across the globe. We're going to pull back the curtain on its core design, navigate its incredibly powerful and unique file system.
Which is quite different.
Oh, yeah. We'll unveil the secrets of its command line and maybe even demystify the art of shell scripting a bit.
Sounds good.
Okay, so let's unpack this. When most people think about operating systems, their minds probably jump straight to Windows or Mac OS, right?
That's the usual assumption.
But lurking quietly in the background, absolutely everywhere, is this true giant, Linux. It's often powering our digital lives without us even having a clue it's there. And it has a really fascinating story of innovation, collaboration, and, freedom.
You've really hit on something vital there. It's a story that encapsulates some of the most fundamental shifts in how software is, conceptualized, how it's created, and ultimately how it's distributed. It set a precedent for so much of the open source movement we see today.
Okay, so to truly appreciate Linux, we probably need to start right at the beginning. Trace the genesis of this quiet digital revolution. So at its core, what is Linux?
Well, at its heart, Linux is what we call a Unix-like computer operating system. But its defining characteristic, the thing that makes it truly unique and, revolutionary, is that it's built entirely on a model of free and open source software development and distribution.
Free and open source.
Exactly. And this isn't just some technical detail. It's a foundational principle. It underpins everything.
So when we talk about Linux, are we mostly talking about the Linux kernel? Is that like the engine, the brain of the whole operation?
Precisely. Yeah, the Linux kernel is the central core component of the operating system. And its origin story is actually quite pivotal in the history of computing.
When did it start?
It's its very first release by a then young Finnish software engineer, Linus Torvalds, back on October 5, 1991.
Wow, 91.
Yeah. And what's particularly intriguing, I think, is the disparity in its adoption. While it absolutely dominates the world of servers, mainframes, and supercomputers.
Right, the big iron.
Exactly. You might be surprised to learn that it actually accounts for a relatively small percentage of desktop computers in the current computing landscape.
Really? That small?
Comparatively, yes. It's the ultimate behind-the-scenes powerhouse, you see. Not always the everyday desktop interface you might click around on.
That's a huge disparity. It really highlights its role as the kind of hidden infrastructure of the internet and beyond. And I've heard there's even been a bit of a naming controversy around Linux itself.
Oh, yes, there certainly has. The Free Software Foundation and the GNU project have had this long-standing and often quite passionate debate over the proper name.
GNU.
That's the one. They often advocate for G in Linux to describe the complete operating system. And the reason is to acknowledge the really significant contributions of the GNU project's components.
Oh.
Because Linus Torvalds relied heavily on those components, especially in the early days of the kernel's development. It really highlights the collaborative nature and sometimes the contentious side of open source development, where credit and philosophy are deeply intertwined.
Interesting. Adds a bit of human drama to it all.
Yeah.
And it even has a mascot, right? Tux the penguin.
It certainly does. Tux makes it feel a bit more approachable, maybe, for such a powerful and sometimes, abstract system.
Definitely.
So, to understand how Linux evolved, we need to go back to Linus Torvalds' early kernel development. He initially began by adapting existing applications that were originally written for an educational operating system called MIX.
MINX. Never heard of it.
It was primarily for teaching OS concepts. But as Linux matured and as Torvalds continued developing the kernel, these early MINAX components were gradually and quite strategically replaced.
Replaced with what?
With free-of-cost code that came directly from the GNU project,
Yeah.
this was an immense advantage for the, fledgling OS. It allowed it to rapidly build out functionality without having to reinvent the wheel, so to speak.
So the GNU project essentially provided this treasure trove of initial building blocks,
Yeah.
a wealth of foundational free code that really helped Linux take off and gain momentum. That sounds like a truly crucial connection in its history.
It truly was. Absolutely critical. And a pivotal moment in this whole journey was Linus Torvalds' decision to switch licenses. He went from his original, more restrictive license, which actually prohibited commercial redistribution.
Oh, really? It wasn't always open for business.
Not initially, no.
Yeah.
He switched to the GNU General Public License, the GPL. Now, this license embodies what are known as copyleft principles.
Copyleft, like copyright, but different.
Exactly. It's a clever legal mechanism. It basically ensures that any software derived from a GPL licensed work must also be released under the GPL. It creates this perpetual chain of freedom, if you will.
Okay, I think I get it. So any improvements have to be shared back.
Precisely. It guarantees that any improvements or customizations you make can be shared back with the community, fostering continuous open innovation and, crucially, preventing anyone from locking down the code and making it proprietary again.
That's clever.
It is. And this is really where the core concept of freedom in Linux began to take its definitive shape. After this license switch, various developers then collaboratively worked to integrate these abundant GNU components with the nascent Linux kernel, creating what truly became a free operating system in, well, every sense of the word.
That's fascinating. So it wasn't just one person's vision, it was this massive, collective, global effort, built on existing free code and then reinforced by this powerful license that ensured its continued freedom and growth. Amazing.
It really is a unique story in software development.
So, with that foundation laid, where is Linux now in terms of its ongoing evolution? Is Linus Torvalds still involved in this massive project today?
Absolutely. Linus Torvalds continues to oversee the further development of the kernel itself.
Okay.
He maintains his role as he's sometimes humorously called the benevolent dictator for life of the project.
Okay.
But beyond his core work on the kernel, there's a truly vast body of work contributed by countless individuals and major corporations. They develop all sorts of third-party, non-GNU components.
Like what kind of things?
Oh, everything from low-level kernel modules that enhance hardware compatibility, making sure it runs on the latest graphics cards or network chips,
Right.
all the way up to user-facing applications that allow millions of people to interact with Linux systems every single day. It's a testament to the incredibly collaborative and just constantly evolving nature of this global project.
This brings us to a really important point, I think, especially for our listeners who might be new to this whole idea. Why does Linux matter to you? What are these freedoms we keep mentioning that make it so distinctive from, say, Windows or Mac OS?
That's an excellent question, and it really cuts to the core of Linux's philosophy. It offers what are often referred to as the four freedoms, which fundamentally distinguish it from most proprietary software you use daily.
Okay, the four freedoms. Let's hear them.
All right. First, you have the freedom to run the program for absolutely any purpose you wish without restriction. You're not limited by what the software vendor decides you can or cannot do with it.
No strings attached on how you use it. Got it.
Second, you have the freedom to study how the program works and, crucially, to make any desired changes. This means the complete source code is openly available.
You can actually look under the hood.
Completely. You can inspect it, learn from it, modify it. Imagine being able to fix a security flaw in your operating system yourself, or tailoring it precisely for your unique needs. That's the kind of empowerment Linux offers.
That's huge.
Third, you have the freedom to redistribute copies to help others. This fosters an incredible sense of community and sharing, allowing knowledge and tools to spread freely without cost barriers.
So you can share it freely.
And fourth, and perhaps most crucially for continued innovation, you have the freedom to distribute copies of your modified versions freely. This ensures, as we discussed with the GPL, that any improvements or customizations you make can be shared back with the community. leading to this continuous cycle of open innovation. It prevents anyone from locking down the code.
That's incredibly powerful. I mean, this isn't just about software anymore. It feels like a radical shift in power dynamics, putting control directly into the hands of the user.
It really is.
It's about transparency, customization, shared innovation, and that really makes you think, doesn't it? How often do you truly have this level of freedom and transparency with the technology you use every single day? It's such a stark contrast to many proprietary systems that keep their inner workings completely hidden.
Indeed. These principles, transparency, customization, community impact, they are fundamental to why Linux has become so incredibly pervasive. It moves way beyond just functionality. It embodies a profound set of values about how software should be developed, distributed, and ultimately used. It fosters a truly unique ecosystem of collaboration.
Okay, so now that we've journeyed through the philosophy and the history of Linux, the next logical step feels like peering beneath the surface. Let's see how Linux actually works its core architecture. How is it built under the hood?
Right. Well, at its core, a Linux-based system is modeled on principles established way back in the Unix operating system, back in the 1970s and 1980s.
This has got a long pedigree.
It does. It follows these time-tested design philosophies for stability and efficiency. Now, the Linux kernel itself uses what's called a monolithic kernel design.
Monolithic. Sounds big.
It means that key components like file system access, network protocols, device drivers, they're either tightly integrated directly into the kernel itself, or they can be dynamically added as loadable modules while the system is running.
Okay, so it's all pretty tightly integrated for performance, but still flexible enough to add pieces as needed without, rebuilding the whole system from scratch.
That's the idea, exactly. Flexibility combined with integration. And, GNU pops up again here as a really foundational element, doesn't it?
Yes, GNU again.
It remains an incredibly important part of most Linux-based systems because it provides the most common implementation of the crucial C library that's fundamental for almost all programs, and a vast collection of common Unix tools that carry out the basic, everyday operating system tasks.
So when I type a command,
chances are much of the underlying functionality you rely on second by second is powered by these robust GNU components. And it's also worth noting that most Linux graphical user interfaces, the pretty windows and icons.
the GUI.
Right, the GUI. They're typically built on top of an implementation of the venerable X Windows system. That's what handles the actual display of windows and graphics on your screen.
Okay, let's break it down then. What are the essential building blocks? The key components that come together to make a Linux system actually tick, starting right from when you hit the power button.
Okay, let's start right at the very beginning of the boot process. First up, you have the bootloader. These are programs like GNU, GRB, probably the most common one, or Suslice UX, or maybe Gummy Boot on some systems. This is the absolute first piece of software that runs when you power on a Linux machine.
The very first step.
The very first. Its critical responsibility is to load the Linux kernel into the computer's main memory, the RAM, and then initiate its execution. It basically sets everything in motion, orchestrating that initial symphony of startup.
Got it. Loads the kernel. And once the kernel is loaded and actually starts running, what's the very next piece of the puzzle? What brings the system to life and gets it ready for me to log in?
That would be the init system. Programs like the traditional sysfinit or more modern ones you hear about like Upstart or Systemed.
Yeah, Systemed. I've heard of that one.
Right. The in system is the very first process launched by the Linux kernel itself. It is, quite literally, at the root of the process tree.
Meaning
every other process that runs on the system is typically launched by or is a descendant of the in system. Its main job is to systematically start all the necessary system services, everything from networking, logging, device management, and eventually present you with those login prompts, either on the text console or the graphical login screen.
Okay, so bootloader loads kernel starts init starts everything else.
That's a good simplification, yes.
Yeah.
Then we have software libraries. What's their critical role in this ecosystem?
Libraries, like reusable code.
Exactly. Software libraries are collections of reusable code that can be easily accessed and utilized by running processes. Now, in Linux systems, particularly those using what's called the ELF format for executables, which is pretty much the standard.
ELF, like the creature.
No, it stands for executable and linkable format. Anyway, there's a dynamic linker, often called ld-linux.so, that manages the loading and use of these shared libraries when a program starts.
Shared libraries.
Yeah, meaning multiple programs can use the same library code simultaneously, saving memory and disk space. Header files are also included alongside these libraries, providing crucial descriptions of the library interfaces. They tell other programs precisely how to interact with the library's functions.
Okay.
And for building the attractive graphical user interfaces for various software applications, you'll find powerful widget toolkits. These provide pre-built components like buttons, menus, sliders. Many notable contributions here come from groups like the Enlightenment team, among others.
Right, the things you actually click on. Now, for the user, how do they actually interact with Linux? Is it mostly clicking buttons, or is it typing commands, or both?
You can effectively do both, and each offers a really distinct experience. Linux offers two primary user interfaces: the command line interface, or CLI, and the graphical user interface, the GUI.
CLI first, the text-based one.
All right. CLI shells are text-based user interfaces. They rely solely on text for both input the commands you type and output the results the system prints back. The dominant shell in Linux, originally developed for the GNU project, is the GNU Born Again shell, universally known just as BASHAC.
BASH, heard of it.
Yeah, this is often where the real power user experience begins, because the CLI is exceptionally well suited for automating repetitive tasks, performing complex system administration, and executing delayed operations or background jobs. It's incredibly efficient once you learn it.
So if you want to automate things, manage the system deeply, scripting, CLI is your go-to.
Definitely.
But for many people, especially maybe those coming from Windows or Mac OS, they expect a visual point-and-click interface. How does Linux handle that graphical interaction?
Okay, so for graphical interaction, Linux systems typically employ a window manager. Its job is to control the placement, the appearance, the behavior of individual application windows on your screen. It interacts directly with the underlying X Windows system, or increasingly Wayland, to draw and manage these elements.
Just the windows themselves?
Primarily, yes. But then, stepping up a level in abstraction, you have desktop environments. Think of things like GNOME or KDE Plasma Desktop.
Ah, those are the big name.
They are. These go a significant step further. They not only include a window manager as part of their standard installations, but they also provide this comprehensive suite of integrated applications, utilities, tools, system settings, panels. A whole shebang.
A whole integrated experience.
Exactly. And they allow for really deep user customization, letting you personalize virtually every aspect of your graphical workspace, from themes to fonts to panel layouts.
Okay.
And then you have modern advancements like the Wayland Compositor. This actually integrates the roles of the display server, the window manager, and the compositing manager all into one efficient piece of software. You could think of it maybe as the artistic director for your screen, ensuring everything looks visually appealing, feels responsive, and is rendered efficiently without screen tearing.
That's a great analogy, the artistic director. It's clear Linux has this robust, layered architecture, really carefully designed for flexibility and power. But how far does its reach truly extend? You mentioned earlier it runs on everything from phones to supercomputers. How is that incredible range of compatibility even possible?
Yeah, that brings us to the really unparalleled hardware support of Linux. And it's directly tied back to its open source and copyleft principles.
How so?
Well, because the Linux kernel, along with its various components, is free of cost and open source software, developers all over the world can freely access, study, and crucially, modify the code.
Anyone can tinker with it.
Anyone. And the copyleft concept, particularly embodied by the GNU General Public License, the GPL, dictates that kind of reciprocity we talked about. Any work derived from a copyleft piece of software must also be copyleft.
The chain of freedom.
That's the one. It ensures the free in free software stays free, creating this perpetual cycle that guarantees any improvements, like adding support for new hardware, can be shared back, fostering continuous innovation. This collaborative, open development model is precisely what allows the Linux kernel to run on such a very high and incredibly diverse range of computer architectures, simply because anyone, anywhere, can adapt it.
It's still mind-boggling to imagine one single operating system kernel spanning such an incredible range of devices. Can you give us some concrete examples? Just how diverse is this hardware support, really?
Well, it's quite remarkable. It truly stretches the boundaries of what a single kernel design can achieve. Linux can run on tiny handheld ARM-based IPQ devices, basically early smartphones.
Right, PDAs almost.
Yeah, all the way up to colossal IBM mainframes like the System Z9 or Z10, machines that process massive volumes of data for huge corporations. This covers a spectrum ranging from the mobile phones and tablets ubiquitous in our pockets today to the most powerful supercomputers on the entire planet.
Phones to mainframes. Wow.
And there are even highly specialized distributions and kernel forks for, let's say, less mainstream or extremely resource-constrained architectures. For instance, there's the ELKS kernel fork.
ELKS.
Yep. It's been adapted to run on much older Intel 8086 and 8286 16-bit microprocessors than ancient PCs. Seriously. Or there's Linux, this microcontroller Linux, specifically designed for systems that don't even have a memory management unit, or MMU, which is common in very small embedded devices.
That's extreme adaptability. And it's not just purpose-built hardware either, is it? I mean, it finds its way onto platforms originally designed for completely different operating systems.
No, not at all. That's another fascinating aspect. The kernel can also be made to run on architectures that were originally intended to use a specific manufacturer-created operating system.
Like what?
Well, believe it or not, Macintosh computers, both older PowerPC and newer Intel ARM models. Various video game consoles, like the PlayStation 3, famously ran Linux for a while. Even different types of mobile phones and portable music players have been made to run Linux by enthusiasts.
So people hack it onto things.
Often, yes. And this wide-ranging compatibility is constantly improving and expanding, thanks to the dedicated efforts of various industry associations and hardware conferences, like Freedom HE, for instance, which are devoted specifically to maintaining and improving hardware support under Linux. And, just to reiterate, the widely used Bash shell, which is your primary interface to the command line, that was also developed by GNU. It all ties together.
So Linux truly is everywhere. Okay, having seen the sheer breadth of hardware Linux can embrace, let's now truly appreciate its omnipresence. Let's look at where Linux comes to life out there in the wild, powering everything from massive data centers to maybe the smallest embedded devices you use every day without even knowing it.
Indeed. It's quite the spectrum. And while many Linux distributions are designed for general purposes, perfectly suited for standard desktops or servers.
Yeah, everyday stuff.
Right. Their inherent flexibility allows them to be highly specialized. This means you find them tailored for an incredibly diverse set of needs.
Like what kind of specializations?
Oh, everything from supporting specific computer architectures, like we just discussed, to enhancing security for sensitive environments, running tiny embedded systems with minimal resources, providing deep localization for a particular region or language.
Localization.
Yeah, making sure all the menus, messages, documentation are in the local language, which open source makes much easier. Also, distributions focused on unparalleled stability for critical systems, or delivering real-time application performance where delays are unacceptable.
Real-time, like for industrial control.
Exactly, or financial trading, things like that. And some distributions even adhere to a strict philosophy, deliberately, including only free and open source software, making a clear statement about digital freedom.
Fascinating. Okay, let's talk about its presence on desktops first. While you said it might be a smaller percentage compared to proprietary systems, its popularity on personal computers and laptops has definitely been increasing, hasn't it?
That's certainly true. The popularity of Linux on standard desktop computers and laptops has quietly but steadily increased over the years. Most distributions today come equipped with a sophisticated graphical user environment.
Like the ones you mentioned, GNOME and KDE.
Exactly. GNOME and KDE Plasma Desktop are two of the most popular and feature-rich options. But it's really important for you to understand that there isn't one singular Linux desktop, in the same way there's a Windows desktop.
Right, it's more of a choice.
Precisely. Instead, desktop environments and the Linux distributions themselves select components from this vast, vibrant pool of free, open-source software to construct their graphical user interfaces. They often implement quite strict design guidelines to ensure consistency and usability.
For example?
Well, the GNOME Projects, for instance, has detailed human interface guidelines that meticulously consider everything from graphical design aesthetics to accessibility for people with disabilities and also robust security features.
Accessibility is built in.
Often, yes, it's a strong focus for many projects. Plus, a fantastic advantage of the collaborative nature of free software development is that it allows for incredibly cost-effective language localization.
You mentioned that easier to translate.
Much easier and cheaper than proprietary systems typically. This means Linux can be made accessible in locales, where localizing proprietary systems might simply not be commercially viable. It really opens up technology to a much wider global audience.
That's a fantastic advantage for global reach and inclusivity. Okay, but where Linux really, truly shines and where most people probably interact with it constantly without even realizing it is in the server space, right? It's absolutely dominant there.
Oh, absolutely. Undeniably. Linux has long been and continues to be the dominant server operating system. It forms the very backbone of the internet and countless corporate IT infrastructures.
Any stats on that?
Well, Netcraft, a well-known internet services company that tracks web server usage, once famously reported, and this was a while ago, but indicative that 8 out of the 10 most reliable internet hosting companies were running Linux distributions on their web servers.
8 out of 10?
It's an astounding statistic that speaks volumes about its stability, its reliability, its robustness. Furthermore, Linux is the undisputed cornerstone of the LAN-MP server software combination.
LAMP.
That's it. It stands for Linux, Apache, the web server, MySQL, the database, and then P for PHP, Python, or Perl, the scripting languages.
Ah, the classic web stack.
Exactly. This powerful stack has achieved immense fame among developers. It's one of the most common, reliable, and cost-effective platforms used for hosting dynamic websites and web applications worldwide. Seriously, if you've ever browsed the internet, retrieved information from a database online, or interacted with an online service, you have almost certainly interacted with an AMP stack powered by Linux.
That statistic really drives home its impact. So, virtually every time you visit a website, you're likely touching a Linux machine somewhere. Incredible. And it's not just web servers, is it? Its reach extends to the absolute giants of computing, too.
No, its presence extends even further into the very largest and most powerful computing environments imaginable.
Yeah.
Linux distributions have become increasingly popular on mainframes in the last decade or so.
Mainframes? Really?
Yeah, partly due to more favorable pricing models compared to the traditional proprietary mainframe operating systems, and certainly because the open source model offers greater transparency and flexibility, which big organizations value.
Makes sense.
And, perhaps most impressively, Linux distributions are universally used as operating systems for supercomputers.
All of them.
Pretty much the vast majority. In fact, for a remarkable decade, right up until the arrival of Japan's Earth Simulator supercomputer, all the fastest supercomputers in the world worked exclusively with Linux.
That's incredible.
This incredible track record speaks volumes about its efficiency, its scalability, and its sheer ability to handle the most demanding computational tasks on the planet. It's built for performance at scale.
That's an incredible testament to its power and efficiency, proving its mettle right at the cutting edge of computation. Okay, beyond the massive servers and supercomputers, you mentioned embedded devices earlier. This is truly where Linux is hiding in plain sight, isn't it? Powering things we often take completely for granted.
That's absolutely spot on. Because of its low cost, often zero licensing cost, its lean resource requirements when configured properly, and its incredible ease of customization, Linux is a massive favorite for embedded systems development.
Like what kind of devices?
You'll find it running tirelessly on non-mobile telecommunications equipment, the stuff in the phone network making calls and data flow smoothly. And on the vast majority of customer premises, equipment hardware. Things like the Wi-Fi router sitting in your home right now, or your cable modem, maybe your smart TV box.
My router runs Linux. Probably.
Very likely, yes. OpenRed, for instance, is a hugely popular community-driven firmware project built entirely on Linux. And many original equipment manufacturers, the OEMs, actually base their own router firmwares on OpenRed or similar Linux foundations.
Wow.
So yes, Linux isn't just on some distant server or maybe your geeky friend's desktop. It's silently powering the devices, connecting your home to the world, making the digital infrastructure all around you just tick.
It's truly ubiquitous. Okay, and then there's the concept of specialized Linux uses. How does that flexibility translate into these highly tailored systems you mentioned?
Well, due to its inherent flexibility, those core freedoms we discussed earlier, and its open source nature, it's remarkably straightforward to highly tune Linux for specific, often very narrowly defined purposes.
How do people do that?
There are essentially two main methods for creating such a specialized Linux system. Either you can build it completely from scratch, carefully selecting and compiling only the absolute bare minimum components needed.
The hardcore way.
Right. Or, more commonly perhaps, you can customize an existing general-purpose distribution. Take something like Debian or Fedora, and then strip away all the unnecessary features, add your specific required ones, and configure it just so.
To make it lean and mean.
Exactly. The overarching goal is always to avoid any resource overhead caused by components that would be redundant or simply not needed in that specific application. This means Linux can be as lean as a tiny single-purpose IoT device monitoring temperature, or as feature-rich as a complex high-end media production workstation for editing video. It's perfectly suited for its intended role, whatever that might be.
That sounds like a genuine superpower for developers and system administrators, truly empowering them to craft exactly the tool they need. Okay, now, if you want to actually harness this immense power yourself, you need to understand how to navigate the Linux world effectively. Let's talk about files, commands, and getting precise control. Where do we start?
Well, a fundamental and really distinctive aspect of Linux is its file system. It's organized in this strict, tree-like hierarchy, consistently starting with the directory, which is universally known as the root.
Root, like the root of a tree.
Precisely. This single root directory is where everything begins. All other files and directories branch out from there.
And this is a key difference from, say, Windows, right? The way it handles drives and storage is fundamentally different.
Absolutely. It's a core concept to grasp early on. Unlike DOS and Windows file systems, which have multiple roots, one for each disk drive, like your C drive or D drive, maybe E for USB stick.
Yeah, separate letters for everything.
Right. The Linux file system instead mounts all disks and partitions somewhere underneath that single unified root file system.
So everything lives under that one /
Everything. Your hard drive partitions, your USB drives, even network shares. They all appear as directories somewhere within that single tree structure. This unified structure is a fundamental difference, and it profoundly simplifies how you think about storage and access paths. Everything appears as part of a single, consistent tree, no matter where it physically resides on what disk.
That actually sounds much more logical.
Many people find it so, yes. It also helps to distinguish between the absolute root of the entire file system, represented by that single / and the separate home directory, specifically for the administrative root user, which is a directory named root.
Ah, okay, so it's the very top, and root is the super user's home folder within that structure.
Exactly. They sound similar, but they're distinct and vital to understand.
Got it. That makes perfect sense. A single cohesive map for all your data. Okay, let's quickly go through some of these key directories under Umbol, because their names and purposes are often quite different from what you might be used to in other operating systems. They're like the essential neighborhoods in this digital city. Certainly. Understanding these is crucial for finding your way around Linux effectively.
This directory contains essential binaries.
Binaries meaning programs.
Exactly. Common programs and executable commands that are shared and used by the system itself, the system administrator, root, and all regular users. Think of these as your core everyday utilities like else, cp, mv, boot. In recent distributions, this critical directory holds all the necessary files for the system to boot up. This includes the Linux kernel itself and often the data for the grub bootloader. This is where the magic happens when you power on your machine.
Makes sense. Dev.
Dev is short for devices. This directory is interesting. It consists of special files that actually represent all your CPU peripheral hardware, your hard drives, your mouse, your keyboard, serial ports, everything. Interacting with these special files allows programs to communicate directly with the hardware.
So devstem might be my hard drive. Typically yes, or something similar depending on the drive type, then etc. Here you'll find important system, etc., mostly configuration files. It's somewhat analogous to the control panel or maybe the registry in Windows. It holds the blueprints for how your system operates.
Etc. for configuration. Got it. Home.
Home. This is a very familiar place for users, as it's where the personal home directories for all common users are located. So you'd have Home Alice, Home Bob, each with their own dedicated space for files.
My stuff goes in home.
Okay. Initerd. This directory usually contains an initial RAM disk image, which is essential for the earliest stages of booting the system, often needed to load drivers for the main storage before the real root file system can be accessed.
A temporary thing for booting.
Pretty much .lib. This consists of essential shared library files needed by the programs in bin and spin, system binaries. These are the code snippets that many core programs rely on to function. There's also strlib for user program libraries.
Libraries for programs. Makes sense.
Yeah.
Lost plus found. Sounds ominous.
A little. In every mounted partition, there's typically a lost plus found directory in its top level. If the file system check utility, SS, finds corrupted or orphaned file fragments during a recovery after a crash or improper shutdown, it places them here. It's like the digital equivalent of a lost and found bin. Hopefully you never need it.
Hope not.
Used for various miscellaneous purposes, often used as a mount point for miscellaneous file systems, maybe temporarily. MP. Traditionally, this was the standard temporary mount point for external file systems, like when you manually mount a USB drive or an external hard disk, though media is often used automatically now. Net. This is often used as a standard mount point for all network-based or remote file systems, like NFS shares.
Opt.
opt. This directory usually contains optional or extra application software packages, often used for third-party software that isn't part of the core Linux distribution, like maybe Google Chrome or proprietary applications.
And root, we covered that the admin's home.
Correct. Root, the administrative user's root home directory. Again, crucial to distinguish this from the root directory of the entire file system. This root is specifically where the most powerful user on the system stores their personal files and configurations.
So it's a very organized, consistent structure, even down to the naming conventions, once you learn them. And the source material mentioned Linux traffic control here too. That sounds like a very granular, deep level of control.
Yes, it's a deeper, more specialized point, but it really highlights the incredible depth of kernel functionality that's available if you need it. The kernel includes sophisticated capabilities like Linux traffic control.
What does that do?
Think of it as a highly advanced air traffic controller, but for your network data packets. It uses specific mechanisms like PRIO classes, queue disks, which stands for queuing disciplines, TBF, token bucket filter, and HFB, hierarchical fair service curve.
Whoa, okay, acronym soup.
Yeah, it gets technical fast. But the point is, these tools allow you to manage network traffic very precisely. You can prioritize critical information, like VoIP calls over bulk downloads, manage bandwidth allocation, shape traffic flow, and ensure smooth data transmission, even under heavy network load. It's a testament to the fine-grained control Linux offers right down at the kernel level.
That's a pretty complex detail, but it definitely highlights the precision possible at the very core of the system. Okay, now for the user who wants to really get their hands dirty, who wants to truly unlock Linux's potential, mastering the command line is absolutely essential. It's your direct control center, isn't it?
It absolutely is. Configuring and interacting with Linux by using the command line is widely considered the most popular and, frankly, the preferred way for power users and system administrators. If you spent any serious time with Linux, whether for personal exploration or professional work, you've undoubtedly encountered and likely come to appreciate the sheer power and efficiency of its command line.
It's where the real work gets done.
Often, yes. It's where precise control meets incredible efficiency.
So, for anyone just starting out, let's cover some basic navigation commands. Can you give us some analogies maybe that make them intuitive and easy to remember?
Great. Let's try it.
Think of this command as your compass. It prints the working directory, instantly telling you your precise location within that vast Linux file system tree. No more guessing, where am I?
PWD tells me where I am. Got it.
Then there's CD, which stands for change directory. This is how you move around, how you navigate through the file system.
Taking you places.
Exactly. Just typing CD on its own with nothing after it will magically transport you right back to your personal home directory. It's a quick return to base.
Handy.
CD directory name will move you into a specified directory, assuming it exists relative to where you are. CD is a convenient shortcut that also takes you to your home directory, meaning you don't always have to type out home username.
Tilde means home.
CD ... lets you move up one directory level, like taking a step back up the tree towards the root. And CD- is neat. It quickly takes you back to your previous working directory, the one you were just in before the last CD. Useful for toggling between two places.
CD up, CD back. Okay.
And to see what's actually in a directory once you get there, you use ls, which stands for list.
Showing you what's there.
Precisely. ls directory name lists the files and subdirectories inside a specified directory. If you just type ls, it lists the contents of your current directory.
Simple enough. But there are options, right?
Oh, yes. LSL gives you a long format list. This shows much more detail. File permissions, the number of links, who owns the file, the group owner, the file size, and the last modified date and time. Very informative.
LS for long.
LS lists all files, including hidden files. Hidden files in Linux are simply those whose names start with a dot. They're usually configuration files you don't need to see all the time.
A for all.
L's old directory name is interesting. The LZ flag tells L's to list information about the directory itself, rather than its contents, when combined with LL. This is useful for checking the permissions and ownership of the directory itself.
LL for the directory info.
And you can use wildcards for pattern matching. For example, L's userbind will list all files whose names begin with the letter D inside the userbind directory, demonstrating the power of pattern matching to find specific files.
Wildcards like the asterisk, okay, those are the absolute basics for navigating, and they already show you how incredibly precise you can be. How does the system actually know where these commands you type, like ls or pwd, are actually located? Is it just guessing? Does it search everywhere?
Not at all. That's managed by your command path. Most commonly used commands, like the ones we just discussed, are stored in specific directories that are included in your shell's path environment variable.
The path variable?
Right. This variable contains a list of directories, separated by colons. When you type a command name, the shell searches through these directories in order, looking for an executable file with that name. The first one it finds, it runs.
Ah, okay. So it knows where to look.
Exactly. Your shell path variable typically includes common locations for programs such as bin, osrbin, maybe us locale bin, and usrx11 r6 bin for graphics stuff sometimes. This means you can simply type the program's name, like ELS, and the shell knows exactly where to find and execute it without you specifying the full bin's path every time.
Makes sense. But what if a command isn't in one of those standard path directories? Like, say, a custom script I just wrote in my home directory.
Good question. If a command isn't in your current path, you'd need to provide its complete location, its absolute path, like home Bob new program. Or if the program is in the directory you are currently in, you can use .program. The dot represents the current directory.
/ means run the thing in here.
Exactly. Or if you have a personal directory for your own scripts, often called bin inside your home directory bin, you might run it with bin program.
So the system knows where to look based on your configured path, like a well-organized library index. Okay, but what about when you want to give specific instructions to a command? Like telling that calculator example earlier what numbers to add or subtract. This is where command line arguments come in, right? The art of making commands dynamic.
Exactly right. This is absolutely fundamental to how interactive command line applications work. After you type a command, followed by some options or file names, those are the arguments that are made available to the underlying program code, typically written in C or another language.
How does the program get them?
In C programs, they're passed into the special main function via two arguments, RGC and RGV. RGC argument count is an integer that tells the program how many arguments were provided, including the command name itself. And RGV, argument vector, is an array of character strings, where each string is one of the arguments you typed.
Okay, count and the actual words.
Precisely. The program's next crucial step is to parse these options, figure out what each argument means, and then run its core logic according to the input provided by the user through specific flags, like NAGI v1, or parameters, like the numbers.
Let's walk through that conceptual example again, the simple calculator, CalChi, because it really illustrates how this works under the hood without getting lost in every single line of actual C code.
Okay, sounds good. So imagine our simple C program designed to act as a command line calculator called CalChi.
Right.
When you run it, maybe like this, .calchi add nash v1 5 dash v2 8.
Okay, add 5 and 8.
The program first checks argc, the argument count. Let's say you need the command name, the operation, the nash v1 flag, the first value, the nash v2 flag, and the second value. That's 6 arguments total. If argc is less than 6, maybe you just type calchi or calchi add, the program would immediately print a helpful usage message.
Tells you how to use it properly.
Exactly. Something like usage, CalChi operation, naja v1, value 1, nash v2, value 2, explaining the correct syntax. This ensures the user knows how to interact with it properly.
Assuming you typed it correctly.
Right. Assuming argc is sufficient, the program internally starts systematically scanning through argc, the array of strings. It typically uses a loop. It looks for keywords like add, sub, mul, or div to determine the operation. It also looks for flags like matv1 and navv2.
How does it know ASCII1 goes with 5?
When it finds the string ASCII1 at a certain position in argv, it knows the next string in the array, at argv a current position plus 1, should be the first value. It takes that string, ASCII5, and converts it from text into an actual integer number, maybe using a function like a toy. It does the same when it finds matv2, getting the next string, 8aver, and converting that.
Okay, it pairs the flag with the next item.
Typically, yes. Once it has successfully identified both the operations, say add, and both numerical values, 5 and 8, it usually exits its input parsing loop.
Got the instructions, now what?
Finally, it performs the actual calculation based on the operation it identified. If it's found add, it adds the two numbers. If div, it divides. And crucially, if at any point during parsing it receives unexpected input, like maybe you type text instead of a number after negative v1, or if it couldn't find both required values, it would signal an error and likely print that usage message again.
Makes sense. It needs valid input.
So for instance, running .calc v1 8 nash v2 90 div might internally calculate 890 and then print something like result equals 0.0888889.
Okay.
.calc d v1 8 nash v2 90 add would yield result equals 98.
Right.
.calc nash v1 8 nash v2 90 mil gives result cas 20.
Yep.
And .calc v1 8 nash v2 90 sub results in result needed 82.
Clear.
This conceptual example, I hope, reveals the meticulous logic happening behind the scenes when you type commands. The program isn't just guessing, it's systematically scanning, validating, and interpreting your instructions based on how it's programmed. Much like maybe a meticulous chef following a recipe step by step, checking each ingredient and instruction before proceeding.
That's a fantastic analogy. It's not magic, it's carefully programmed parsing that gives Linux commands their power and flexibility. Okay, and once you grasp that basic idea of commands and arguments, you can move to even more precise control using these special Linux control operators. These are special characters that tell the shell itself exactly how to execute commands, allowing for really complex command sequences, sometimes all on a single line.
Exactly. These operators are incredibly powerful, especially for scripting and more advanced command line usage. Let's go through them. The semicolon is probably the most straightforward. It's used simply for separating two or more commands written on the same line. It tells the shell, run the first command, wait for it to finish, then run the second command, wait for it, and so on.
Just runs them one after another.
Yep. For example, echo John. Echo Sam will first print John to the screen, then once that's done, it'll print Sam on a new line. Simple sequential execution.
Okay. How about the ampersand? That one seems useful for like efficiency or multitasking.
It absolutely is. The ampersand, when placed at the very end of a command line, is powerful because it tells the shell to run that command in the background.
In the background. Meaning?
Meaning the shell will not wait for that command to finish executing. Instead, it immediately returns control to your terminal prompt, allowing you to type new commands right away, while the original command continues to run discreetly behind the scenes.
Ah, so it doesn't tie up my terminal.
Exactly. If you type, say, sleep 20, sleep just pauses for a number of seconds. The system will instantly give you back your command prompt, maybe showing you a job ID like 13124, indicating it's job number 1 with process ID 3124, and the sleep command will quietly count down for 20 seconds without stopping you from doing other work. This is how you keep working while a long-running task, like a big file copy or a complex calculation, runs without interrupting your workflow.
That's incredibly useful for long processes. Okay, what about AJ Dull? The dollar question mark. That sounds like something for debugging or scripting.
It's precisely that. A cornerstone of scripting. The dollar question mark is a special shell variable that holds the exit code or return status of the very last command that finished executing.
Exit code.
Yeah. By convention, an exit code of 00 universally indicates success the command completed without any errors. Any non-zero value, typically 1 or higher, indicates that some kind of failure or error condition occurred during the command's execution.
So 0 is good, anything else is bad.
Generally speaking, yes.
Right.
For example, if you run touch file 1, which successfully creates an empty file named file1, then immediately type echo $, the shell will print 0.
Success.
Right. If you then run arm file 1, which successfully removes the file, and type echo $, again, you'll still get 0 because the arm command also succeeded.
Okay.
But if you try to run arm file 1 again after the file has already been removed, the arm command will fail. You'll probably print an error message like arm.cannot remove file 1, no such file or directory. And then if you type echo $, the shell will print 1 or some other non-zero number, indicating that the last command failed.
Ah, I see. It tells you if the last thing worked or not.
Exactly. It's absolutely crucial for scripting because it allows you to build complex logic like if the previous command succeeded, then do this, otherwise do something else.
Okay, so it's about checking success. What if you want to chain commands based on that success? Like run the second command only if the first one actually succeeded, maybe to prevent an operation from running if a prerequisite step failed.
For that specific scenario, you use the double ampersand. This operator signifies conditional execution based on success. The logic is, run the first command. If and only if the first command succeeds, returns an exit code of 0, then proceed to execute the second command.
And if first one fails?
If the first command fails, returns a non-zero exit code, the entire sequence stops immediately. The second command is not executed at all, and the shell usually reports the failure status of the first command.
Example.
Okay. Echo John and echo Sam.
Since echo John always succeeds, returns 0, the shell proceeds to run echo Sam. So you'll see both John and then Sam printed.
But now, consider echo John and echo Sam. Assuming Echo is not a real command on your system, the shell will try to run it, fail, and probably turn an error like bash.echo command not found. Crucially, because the first command failed, the echo condition is not met, and the echo Sam part is completely skipped. Sam will not be printed.
Clear as day. That prevents a lot of potential headaches in automated scripts. Okay, the pound sign, hashtag next. That seems like a universal standard in programming for comments.
Indeed it is. Very straightforward. The pound sign, hashtag, also called hash or sharp, is used for comments in shell scripts, and often on the command line, too. Anything on a line that follows a hashtag is completely ignored by the shell.
It just skips it.
Completely skips it. It has absolutely no influence on command execution. It's purely there for human readability. It allows you to add explanations for complex commands, notes to your future self or colleagues, or maybe temporarily disable a line of code in a script without deleting it by putting a hashtag at the beginning. Mm-hmm. You might see something like mkdir test2, hashtag we create a directory called test2. It's your way of leaving notes, documenting your thought process within the code itself.
Simple but essential for clarity. And finally, escaping special characters. That sounds like you're telling the shell, hey, don't treat this special symbol like a command, just treat it like plain text.
That's exactly what it's for. The backslash is the escape character in Bash and many other shells. Its purpose is to remove the special meaning that certain characters normally have to the shell, forcing the shell to treat them as literal characters instead.
Why would you need to do that?
Well, many characters have special meanings. We just talked about hiss, end-ended and loyal, hashtag. Others include the asterisk, question mark, square brackets, parentheses, spaces, single quotes, double quotes, and the backslash itself. If you want to use one of these characters literally in a command or string, you often need to escape it.
Examples.
Okay. If you wanted to print the literal string, John, Sam, including the semicolon, you couldn't just type echo John, Sam, because the shell would interpret the semicolon as a command separator. Instead, you'd type echo John, Sam. The backslash tells the shell, treat this semicolon as just a character, not a separator.
Oh, okay.
Or if you wanted to put multiple literal spaces between words, the shell normally condenses multiple spaces, you might use echo John. Each inserts a literal space. You can also use it to escape quotation marks if you need to include them inside a string defined by the same type of quotes, though using alternating quote types is often easier. For instance, echo, he said hello, uses backslashes to include literal double quotes inside a double-quoted string. You can escape the escape character itself, produces a single literal backslash, or other special characters like echo escaping. This allows you to precisely control your output and treat characters normally reserved for powerful shell commands as just regular text when needed.
That's a remarkable amount of precision control available right at your fingertips when you're interacting with Linux at the command line. Okay, now let's power up and talk about the core interface itself. Bash, maybe other shells, how commands can be connected together, and the incredible power of automation through scripting. First, what exactly is a command shell, in simple terms, just to be clear?
Right. So a command shell is essentially a program that acts as an interpreter for the commands you type. It allows the user to execute instructions, either by typing them manually in an interactive terminal window or by automatically running them from programs known as shell scripts.
So it's the middleman.
You could think of it that way. Crucially, a shell is not the operating system itself, not the kernel. Rather, it's a vital type of user interface that translates your instructions into actions that the underlying operating system kernel can understand and perform.
Got it. The translator. And Bash, the born-again shell, that's the default and most widely used shell in the Linux world. Correct?
Correct. BAH, or born-again shell, is a very powerful and, importantly, free software replacement for the original standard Bourne shell, which was widely used in older Unix systems.
Born again, like born again.
Huh. It's a bit of a pun on the original creator's name, Stephen Bourne. Anyway, Bash incorporates pretty much all the features of the original Bourne shell, plus a whole wealth of additional features that make it significantly easier and more intuitive to program with for scripting, and also to use directly from the command line interactively.
What kind of extra features?
Things like command history, recall using arrow keys, tab completion for commands and file names, better job control for managing background processes, more advanced scripting capabilities like arrays, and better arithmetic. Lots of quality of life improvements.
Okay.
And because it is free and open source software, it was very widely adopted as the default login shell for various Linux systems early on, and it's almost certainly the one you'll encounter most often when you first open a terminal window in Linux today.
So, for anyone maybe used to the DOS or Windows command prompt, cmd.exe or PowerShell, which many of our listeners might be, what are the key differences they really need to be aware of when they first step into the BASH environment? It's not quite the same ballpark, is it?
No, it's definitely not. There are a few fundamental differences that are absolutely critical to understand right from the outset to avoid confusion. First, and this trips up many people, case sensitivity.
Upper versus lower case matters.
Immensely. In Linux, commands, file names, directory names, variable names, pretty much everything is very case sensitive. Typing excite t instead of exit will simply result in a command not sound error. myfile.txt is considered a completely different file from myfile.txt. Windows, by contrast, is largely case insensitive.
That's a big one to remember. Okay.
Second, slash versus backslash. This is often another major point of confusion. In Linux and Unix, the forward slash is the universal directory separator used in file paths, like homeuserdocuments_report.txt. The backslash in Linux is reserved exclusively as an escape character, as we just discussed. This is completely opposite to how the backslash is used as the primary directory separator in DOS and Windows. For example, users user documents.
/ for paths, / for escaping. Got it.
Third, file names. Linux file names are much more flexible and robust than older DOS systems. There's no inherent 8-character limit followed by a 3-character extension, the old 8.3 format. You can have much longer, more descriptive file names, and they can contain multiple dots. The concept of a single extension isn't really enforced by the OS itself, though conventions exist.
More freedom in naming files.
Yes. And fourth, command syntax. While there are some conceptual similarities, the general structure for Linux commands is highly consistent and powerful, typically following the pattern. Command -options, long options, arguments files. Options often modify the command's behavior. For example, L simply lists files.lsl lists files in a long format using a short single dash option. And LSL color auto might provide a colored output using a longer double dash option, enhancing readability. Similarly, cat file name shows the content of a file, while catxn file name shows the content along with line numbers using the lns option. Understanding these fundamental differences, case sensitivity, slashes, file names, and command structure really helps you navigate the Linux environment with confidence and avoid common pitfalls.
Those are definitely critical distinctions for anyone making the jump from Windows. Okay, now let's talk about connecting commands together, which is where Linux and Bash really start to show their incredible power and elegance, piping and redirection. What exactly is the pipe operator, the vertical bar OR, and how does it revolutionize how you use commands?
The pipe, represented by that vertical bar OR, is honestly one of the most elegant and powerful features of the Linux and Unix shell philosophy. It's used for creating a chain of 2 or more commands, where the standard output of one command is literally piped or redirected to become the standard input of the very next command in the chain.
Output of one becomes input of the next.
Exactly. If there's a second pipe in the sequence, the output of the second command is then sent to a third program, and so on. It's like creating a mini data processing assembly line right there on your command line, where each command performs a specific task on the data and passes its processed result to the next tool in the line.
Can you give us a concrete example? Show us how the pipe transforms a simple command into a more powerful workflow.
A very common and practical example is dealing with long command outputs. Let's say you run let_lbren. The userbin directory contains hundreds, maybe thousands of programs. Running let_lr generates a long format list of all of them, including hidden ones. This output can be incredibly long, right?
Yeah, you would just scroll off the screen instantly.
Exactly. It would fly by before you could read any of it. This is where the pipe comes in beautifully. You type let_lbren less.
Pipe to less.
Right. Here's how it works. First, the shell runs let_lbren. Instead of printing its output directly to your screen, the pipe intercepts that entire, potentially massive stream of text output. It then redirects that output and feeds it directly into the standard input of the less command.
And what does less do?
Less is a pager program. It takes that input stream and intelligently displays it to you one screen full or page at a time. You can then use keys like page up, page down, the arrow keys or spacebar to scroll through the output at your own pace. You can even search within the output using followed by a search term. When you're done, you just press Q to quit less.
So it makes massive output manageable.
Precisely. This is incredibly powerful for combining simple, focused commands, like else to list, grep to search, sort to sort, into complex, manageable workflows, preventing information overload and allowing you to process data step by step.
That's a workflow accelerator right there, turning a potential fire hose of information into a readable, searchable stream. Okay, what about redirecting output not to another command, but directly to files? That sounds essential for things like logging or saving results.
That's another extremely useful capability for managing data flows. It's often incredibly helpful, as you say, to save the output of a command directly into a file instead of just having it displayed momentarily on the screen. There are two main ways to do this.
Okay.
You can use the single greater than character to overwrite a file with the command's output. For instance, lslsl home vis mp4.mp4 mp4files.txt will run the ls-l command to list details of all mp4 files in a specific directory. Instead of printing to the screen, the send to shell to take that entire output and save it into a new file named mp4files.txt in the current directory.
And if mp4files.txt already exists...
Critically, if mp4files.txt already exists, its current content will be completely wiped out and replaced with the new output from the mplos command, the overwrites.
Okay, overwrites. What if I want to add to the file, not replace it?
If you want to add new output to the end of an existing file without deleting its current content, you use the double greater than characters to append.
Appends.
Right. So following the previous example, if you then ran lal home vis extra mp4s.mp4 mp4files.txt, this would list any mp4 files from a different directory, extra mp4s, and append that list to the end of the existing mp4files.txt file, preserving whatever's already written there from the first command. Imagine the power of easily logging command outputs over time, or compiling detailed reports by progressively adding information using these simple yet incredibly powerful redirection operators.
That's huge for automation, record keeping, and maybe even building simple data pipelines right from the command line.
Okay, speaking of working with files and directories, what's the core tool set for actually managing them in Linux? These are probably some of the most frequently used commands day to day.
Indeed. Linux provides a comprehensive suite of fundamental commands for file and directory management, each serving a specific, indispensable purpose. For understanding files, you have the file command. You give it a file name, and it tries to determine what kind of file it is based on its contents. Is it a text file, an executable, an image, a PDF? Very useful.
File tells you the type.
For displaying file content, you have several options. Cat, short for concatenate, usually displays the entire file's content to the screen at once. Head shows you just the beginning lines of a file. Dample is 10 lines, but you can specify, like head -n20. Tail shows you the ending lines. Again, default 10, tail -n5 shows the last 5.
Cat all, head top, tail bottom. Exactly. And a particularly useful variant is tail-f file name. The dash flag means follow. It shows the last few lines of a file and then continuously monitors the file, printing any new lines that get appended to it in real time. Absolutely perfect for watching log files as events happen.
Tail-f for live updates. Cool.
For copying, moving,
Yeah.
which is also renaming, and removing files, you have the classic intuitive commands .cp, copy on, mv, mover name, and rm is delete. Be careful with a fire, especially with wildcards, as there's usually no undelete.
CP, MV, RM, standard stuff. Directories.
For directories, mheadir is used to make a new directory, and rmengr is used to remove an empty directory. To remove a directory in its contents, you typically use rm-r recursive remove.
Okay, basic file operations covered. Now, how do you actually find things in this potentially vast tree-like file system? If you don't know exactly where a file is, it can feel like finding a needle in a haystack sometimes.
True, but luckily Linux gives you several powerful tools for finding files and commands.
This command tells you the full path to a particular shell command that would be executed if you typed its name. For example, which DRLs might tell you it found binels. It basically shows you what the shell's path search finds first.
Which finds commands in the path.
Whereas, this command is a bit broader. It helps you locate the binary executable, the source code if available, and the manual pages for a given command.
Whereas finds more stuff related to a command.
Locate. This command provides a very quick file search across your entire system. It usually works by searching a pre-built database of file names that's updated periodically, often daily. Because it searches a database, it's incredibly fast for finding files by name, but it won't find files created since the last database update.
Locate is fast, but might be slightly outdated.
Right. And then there's find. This is the most powerful and versatile, though also arguably the most complex, search command. Find actively searches the directory tree, starting from a specified point. It allows you to find files matching incredibly specific criteria, not just name, using complex patterns, but also size, modification time, ownership, permissions, file type, and much more. You can even execute other commands on the files it finds.
Find is the super powerful complex searcher.
Exactly. It's your ultimate detective toolkit for navigating the vast Linux file system, allowing you to pinpoint exactly what you're looking for no matter how obscure the criteria.
Okay, that's a solid set of search tools. Now, beyond just files, what about getting crucial information about your system's current state? Its performance, running processes, memory usage. These are the commands that really give you the pulse of your Linux system, right?
Absolutely. Monitoring system health is critical. We have several key informational commands for that.
This command process status. It lists currently running processes on your system. By default, it might only show processes started from your current terminal, but with options like pvso or psef, you can see all processes running on the system. This is your window into what your computer's actively doing right now.
Beef shows processes.
W. This command shows who is currently logged into the system and what each logged in user is currently doing, which command they are running in their foreground. It also shows system uptime and load averages.
DU shows who's logged in and what they're doing.
DFF simply prints your current user ID, UID, group ID, GID, and any supplementary groups you belong to. Helpful for understanding permissions and identity.
ABS shows my user info.
DSS stands for disk free. This command shows you the file system disk usage, giving you an overview of how much space is used and available on all your mounted partitions. Often used with EH for human readable sizes, like MB or GB.
DF for disk space overview.
DO stands for disk usage. This command estimates and displays the disk space used by a particular directory and its contents recursively. Useful for finding out what's taking up space. Often used with H, human readable, and summary total.
For specific directory size.
This is a classic. It provides the dynamic, real-time updating display, almost like a text-based GUI, showing all running CPU processes. They're typically sorted by CPU usage by default, allowing you to instantly see what's consuming the most resources. It also shows memory usage, uptime, load average. It's like a live performance dashboard for your system.
Top is the live dashboard.
Free. Shows you the total used and free amounts of physical RAM and swap memory in your system. Again, HH makes the output easier to read.
Free for memory usage.
Have cat proc poinfo. This isn't a command itself, but rather reading from a special file in the proc virtual file system. It displays detailed information about CPUs in your system model, speed, cache size, cores, etc.
Proc has system info files.
Yes. Proc is full of useful real-time system information presented as files. And finally, unname. Prints comprehensive unname, Unix name, information about the Linux kernel you are running, including its version number, the machine hardware architecture, like a x86-64, the host name, and the OS name. The means show all information. These commands collectively give you the complete pulse of your Linux system, helping you monitor its health, performance, and activity.
That's a full diagnostic kit right there at your fingertips. Any other common, useful utilities you'd quickly recommend people learn?
Yes, absolutely. Some other very commonly used utilities include clear to simply clear the terminal screen for a fresh start, echo to display text strings or variable values to the screen. More and less, as we discussed, for displaying file or program output one screen at a time. Less is generally more powerful. grep is essential. It searches for specific patterns within text input or files, LPR or sometimes LP, to send a file to a printer. Sort to sort lines of text files or output alphabetically or numerically. And su, substitute user, or sudo, super is or do, to temporarily switch user accounts or run commands with administrative privileges.
grep for searching text, sort for sorting, sudo for permissions.
Got it.
And for boosting efficiency, what are some key command shortcuts? Things to speed up typing all these commands. These sound like they could be real game changers for productivity.
Oh, they absolutely are. Mastering these shortcuts can dramatically increase your speed and efficiency at the command line. They transform you from just a typist into a Linux maestro. The up and down arrow keys. These are fundamental. They allow you to instantly scroll through your command history, the commands you've recently typed in that session. You can bring back a previous command, edit it if needed, and re-execute it without retyping the whole thing.
Up, down for history. Essential.
History. Typing the command history on its own shows you your complete command history list, usually numbered, allowing you to see commands from further back or across sessions, depending on configuration.
History shows the list.
Tab completion. This is arguably the biggest time saver. By typing the first few characters of a command name, a file name, or a directory name, and then pressing the tab key, the shell will attempt to automatically complete the rest of the name for you. If there's only one possibility, it completes it instantly. If there are multiple possibilities, pressing tab a second time will usually list them all for you. It saves countless keystrokes and avoids typos.
Tab completion is magic.
Yeah.
Yes. The exclamation point, or bang, offers powerful history recall. You can type dot, followed by a number, for example, 123, to re-execute the command with that specific number from your history list. Or you can use string, for each L, to execute the most recent command in your history that started with that specific string. Re-executes the immediately preceding command. Use with caution.
Bang for history recall.
Oh,
okay.
C-LR. This is incredibly powerful for searching. It initiates a reverse incremental search through your command history. As you start typing characters, it shows you the most recent command in your history that contains those characters, updating as you type more. Once you find the command you want, you can press Enter to execute it or arrow keys to edit it. It's fantastic for finding complex commands you used previously but can't quite remember fully.
CTLL searches history. Nice. Shift plus page up, shift plus page down. These keys usually let you scroll up and down through your terminal's output buffer, the text that has already been printed to the screen, potentially scrolling off the top. This is invaluable if a command produced a lot of output you need to review. The exact keys might vary slightly depending on your terminal emulator program.
Shift plus page up down scrolls the screen buffer. Okay.
Mastering these shortcuts honestly makes working on the command line so much faster and more fluid.
These shortcuts absolutely sound like game changers. Okay, this all leads perfectly into one of the most powerful aspects of Linux. Shell scripting. This is where you move from just using Linux commands interactively to truly making Linux work for you, automating complex sequences of tasks, and essentially building your own custom tools. What exactly is shell scripting, fundamentally?
Shell scripting is, fundamentally, the practice of writing a series of Linux commands and programming constructs, like loops, conditions, variables, together in sequence, typically stored inside a plain text file. This file, the script, can then be executed by the shell, which reads the commands line by line and runs them.
So it's like a batch file in Windows, but more powerful.
You could say that, yes. It's conceptually similar, but generally much more powerful and flexible due to the rich set of commands and the shell's programming features. It's an absolutely cornerstone skill in the Linux programming and administration environment, essential for anyone managing or developing on Linux systems.
Why is shell scripting so important? What specific problems does it solve for users and administrators? What's the real need for it?
There's several key reasons why shell scripting becomes indispensable very quickly. First, it allows you to create interactive tools by taking input from the user, reading variables, and providing formatted output back to the screen. Echo, print.
Making custom interactive tools.
Second, you can effectively create your own powerful, custom power tools by combining multiple existing Linux commands and utilities, maybe piping them together, all within a single executable script. Turn a complex multi-step process into a single command.
Building your own commands.
Third, and perhaps the most common and compelling reason, automation. It excels at the automation of repetitive command input and entry. Instead of manually typing the same sequence of 10 commands every morning to check system status or process some data, you write a script once and just run that single script whenever needed. Saves huge amounts of time and reduces errors.
Automation of repetitive tasks. Key benefit.
Fourth, it's incredibly useful for customizing and standardizing administrative tasks. Things like setting up new user accounts with specific directory structures and permissions, backing up critical data according to a defined schedule and procedure, rotating log files, managing system services. Scripting makes these reliable and consistent.
Customizing admin tasks.
Fifth, you can even create surprisingly robust, albeit simple, applications entirely with shell scripts, especially for quick utility tasks, data transformation, or system monitoring tools.
Creating simple apps.
And finally, related to automation, because scripts are typically well-tested and standardized, the chances of human errors creeping into complex configuration changes or routine system administration tasks are significantly reduced. It brings consistency and reliability to operations.
So it really boils down to making your life easier, more consistent, more productive, and less error-prone. What would you say are the main advantages of using shell scripting?
The advantages are numerous and quite compelling. They're relatively easy to use, especially if you're already familiar with the basic Linux command line tools. The learning curve isn't too steep initially.
Easy to get started.
You can get started very quickly, often writing useful, simple scripts within minutes to solve an immediate problem.
Quick start.
They offer interactive debugging. You can easily run parts of your script directly on the command line, or add echo statements to see variable values, or use shell options like bash script.sh to see every command being executed.
Interactive debugging.
As we said, they save an immense amount of time by automating tedious, repetitive tasks.
Saves time. Huge plus.
They are absolutely essential for system administration automation, handling routine maintenance, deployments, monitoring, etc.
System admin automation.
And they can often be modeled and prototyped very quickly without needing complex compilation steps or development environments like you'd need for C or Java, just a text editor and the shell.
Easily modeled prototyped. Okay,
Yeah.
sounds great. Any significant downsides or limitations to shell scripting that users should be aware of? It can't be perfect for everything, right?
No, you're right. It's not a silver bullet. There are a few considerations and potential downsides. Compatibility issues can sometimes arise. While BHH is widely standardized, different Linux or Unix-like systems might have slightly different versions of commands or shell features. Or users might be using a different shell altogether, like Zush or Fish. Scripts aiming for broad portability need careful testing.
Compatibility across platform shells.
Execution speed can be slower compared to compiled languages like C, C++, AB, Go, or even interpreted languages like Python for very CPU-intensive tasks. The shell interprets each command line by line, often launching separate processes for external commands, which has overhead. For high-performance computing, shell scripts usually aren't the first choice.
Slower execution speed for heavy tasks.
And related to that, for very complex tasks involving lots of subprocesses or function calls, the way the shell sometimes needs to reinitialize environments or re-execute parts of itself can occasionally impact performance or lead to unexpected behavior compared to a monolithic compiled program.
Overhead for complex code subprocesses. Okay, good to keep in mind. Now let's talk about shell variables. These seem crucial for making scripts dynamic and adaptable, allowing them to work differently based on input or environment, right? How do you view them, and what are some common important ones that power the shell itself?
Shell variables are absolutely fundamental, yes. They're used for storing and manipulating data within scripts and the shell environment, allowing scripts and commands to adapt to different situations or user inputs. You can view the variables currently set in your shell using a few commands.
This command typically shows all shell variables, including variables you've defined yourself, as well as internal shell options and functions. It can be a very long list.
Set shows everything.
Enhemve or inpentrenve. These commands usually show only the environment variables. These are variables that are typically inherited by any child processes launched from the shell. They define the working environment.
Imprint and Venturable for environment variables.
Right. Some common and important shell environment variables you'll frequently encounter include
Often holds the full path to the bash executable itself, like bin bash.
contains the network name of your computer. Useful for logging or scripts that behave differently on different machines.
Similar to path, but this defines a colon-separated list of directories searched by the cd command when you try to change to a directory without specifying a full path, starting with or dof or def.
Specifies the path to the file where your command history is saved between login sessions, typically something like bash history, his file size, his size. Control the maximum number of lines, commands, stored in the history file and kept in memory during a session, respectively.
This is fundamental. It holds the absolute path to the home directory of the current user, v.g. homealias. Scripts often use this to find user-specific files.
As we discussed, this critical variable holds the colon-separated list of directories the shell searches when you type a command name, telling it where to find executable programs.
Specifies the type of login terminal you're using. Example, exterm 256 color Linux. This affects how programs format their output for your screen.
Usually sets the path to your default login shell. Example, bin bash.
Crucial for graphical applications running under the X Windows system, or Wayland sometimes. It tells GUI programs which screen display to connect to, usually something like 0.0 for the primary local display.
Okay, so these variables give your scripts and the shell itself context and access to critical system information, making them much more intelligent and adaptable. And when you actually want your script to say something to display output to the user or present information, you primarily use echo or print, is that right?
Precisely. Those are the two main workhorses for generating output in shell scripts. Echo is your go-to for simple text display. It's straightforward and perfect for status messages, prompts, or basic variable output.
Can we look at that conceptual backup script example again to see how echo works in practice?
Sure, let's revisit that idea. Bash, hashtag simple conceptual backup script, echo backup shell script starting hashtag simple message. Echo hashtag prints a blank line for spacing. Hashtag use command substitution to insert dynamic info. Echo runtime, dis8 on host. Hostname.echo. Runtime, echo runtime. Hashtag defines variables, echo runtime. Backup dir, NAS05 backups. Hashtag where to store backup, echo runtime. Now, date plus %, dollars for geography, as or 1%. Hashtag dollars timestamp for unique folder name. Echo runtime. Target dir. Backup door now. Hashtag full path to this backup run. Echo runtime. Hashtag let us simulate to start the backup process. Echo creating backup directory. Target A. Echo creating backup directory. Hashtag mp ntdir-b. Target dir. Hashtag real command would be here. Echo create backup directory. Echo dumping MySQL database.sql. Hashtag real command. Echo. Hashtag echo compressing database dump. Echo creating backup directory. Hashtag tar czf. Target a latest db backup.sql. Target dir database.sql. Hashtag real command. Echo creating backup directory. Sleek 33 chag. Just pause for 3 seconds to simulate work. Echo creating backup directory. Echo hashtag print another blank line. Echo backup seemingly complete. Archive would be at target di ripdb-backup.tar.gz.
Okay, break that down. How is echo being used there?
All right. You see simple echo, backup shell script, starting now just displays that literal text message. Echo on its own prints a blank line, which is useful for formatting the output nicely. The UC echo runtime state on the host names of the syntax is called command substitution. The shell first runs the command inside the parentheses, date or host name, captures its output, and then substitutes that output directly into the echo command string before printing it. So it dynamically inserts the current date time and the system's host name into the message when the script runs.
So command runs the command and puts its output right there.
Exactly. We also define variables like backup dir and moww. Then later echo commands use these variables, like target dir, to customize the messages further, showing the user where the backup is supposedly being created or saved. It demonstrates how echo combined with variables and command substitution makes your scripts talk to the user, providing dynamic updates and relevant information about their progress.
That's a really practical example of echo for general communication and status updates. Okay, what about print then? You mentioned it's for more controlled, formatted output, almost like generating a spreadsheet row or structured report line.
Yes, exactly. Print offers much more granular control and highly formatted output capabilities, very similar in concept and syntax to the print function found in the C programming language, which many programmers are familiar with. It's incredibly powerful for presenting data in a very structured, aligned, and precisely formatted way. It uses special format directives, placeholders, and interpreted escape sequences.
Escape sequences, like N for new line.
Exactly. Interpreted sequences include things like N for a new line, T for a horizontal tab, for a literal backslash, for a literal double quote. You can also represent characters using octal, 0NN, and or hexadecimal xtodes, or even Unicode, UXXXX. Percent is used if you simply want to print a literal percent sign, because percent itself is used to start format specifiers. And there's a special sequence per C, which tells printf to treat the corresponding argument as a string, but then interpret any backslash escapes within that string argument itself, giving you very fine-grained control over tricky output.
Okay, and the format specifiers, those are the placeholders like in C.
They are. Format specifiers are the heart of print's power. They tell print precisely how to format the corresponding variable or value when displaying it. The most common ones are percents for a string of characters. Yeah. Percent for us deviture, or percent for us for an integer, a whole number, decimal format. Percent for a floating point number, like 3.14159 in standard decimal notation. Percent or percent form, percent int4 for a floating point number displayed in scientific exponential notation, like 3.14159e plus 00.
Percent string, percent integer, percent float.
Got it. There are others too, like percent for a single character, percent for octal integers, percent or percex for hexadecimal integers, but SD and F are the most common.
Can you give us an example of how print text can be used to format text and numbers precisely? Maybe demonstrating the control over width and decimal places that echo doesn't easily give you?
Certainly. Let's imagine we have some shell variables set up. Product, laptop, quantity 5, price, 1200.50, and maybe a very long serial. 987654 3210 12345.
Product. This is simple, like echo. It prints product, laptop, followed by a new line. Now let's control the width for alignment. Pints quantity, percent ends product. Quantity, product. Quantity might print product. Laptop quantity 5. Notice the pin allocates 10 characters for laptop, right aligning it by default. This helps line up columns. Percent 10's quantity, percent 10. Product quantity, adding the minus sign makes it left align. Product, laptop quantity 5. We can also control precision. Printf, first 3 letters. 3SN to product, print first 3 letters. Lap. The point 3 limits the string output to 3 characters.
Percent 3 to 3 units, and there is quantity, might print quantity. 005 units. The O3 means print as a decimal D, with a minimum width of 3 characters, padding with leading zeros if needed. For our large serial number, print serial scientific might output it in scientific notation, like 9.876543E plus 12, and for a floating point price.
Print price would probably give price 1200.500.00000. Print often defaults to 6 decimal places for percent, but using print price, 6%, $2.11, we get the much more useful price, $1,200.50. The point 2 before the F specifies exactly 2 digits after the decimal point, perfect for currency.
Ah, okay. That .2F is exactly what you need for money.
Exactly. This really demonstrates how print gives you that granular, precise control over exactly how your script presents information, controlling width, alignment, padding, decimal places. It's ideal for generating nicely formatted reports, tables, structured log messages, or any output where appearance and alignment matter.
That's incredibly powerful for generating clean reports or highly formatted output right from a script. Okay, finally, let's zoom out and explore the Linux family itself. Because it's not just one single thing called Linux, it's this vast, incredibly diverse world of different distributions, or distros as people call them. Each seems to have its own flavor and purpose.
That's absolutely right. It's truly one of the most remarkable and defining aspects of the entire Linux ecosystem. While, yes, many Linux distributions are designed for general purposes, perfectly capable of running on desktops and servers alike, offering a broad set of software.
Big all-rounders.
Right, but the open source model allows for, and indeed encourages, incredible specialization. This means that distributions are often highly tailored for various specific needs or philosophies.
We touched on some specializations earlier.
We did. You find distros focused on ensuring broad computer architecture support, running on ARM, PowerPC, mainframes, etc. Others concentrate intensely on security features, hardening the system for sensitive environments. Many are designed specifically for tiny embedded systems with very limited resources. Some prioritize deep localization for a particular region or language community. Others value stability above all else, using older but extremely well-tested software packages ideal for critical servers. Still others are optimized for real-time applications where predictable, low-latency performance is paramount.
You mentioned the philosophical ones.
Yes, and some distributions adhere to a strict ideology, deliberately including only free software, as defined by the Free Software Foundation, making a clear statement about digital freedom and avoiding any proprietary drivers, firmware, or applications.
A huge variety. And within this family, Debian seems like a major player, right? Almost like a foundational distribution that many, many others are built upon. It feels like the grandparent of a massive family tree.
Absolutely. Debian has a monumental legacy in the Linux world. It's known for its stability, its huge software repositories, its strong commitment to free software principles, and its robust package management system, apt. It serves as the stable, reliable base for an incredibly wide variety of other distributions, each building on Debian's strengths while adding their own unique flavor, focus, or target audience.
Okay, so let's dive into some of those fascinating branches of the Debian family tree. Can you give us some examples and what makes them unique?
Certainly, the Debian derivatives are incredibly diverse. Let's start with 64 Studio. This distribution was specifically tailored for audio and video production work, providing a pre-configured environment with relevant software and optimizations for creative professionals using 64-bit by 86 systems.
For the media creators.
Aptocid. This was known for being a multilingual, desktop-oriented live CD-DVD that was based directly on Debian's often bleeding-edge unstable branch, codenamed SID. It offered users very fresh software packages while still retaining much of Debian's infrastructure and reliability.
Cutting-edge Debian.
Astra Linux. Now, this is a truly fascinating example. Astra Linux is an operating system developed in Russia, specifically commissioned for use by the Russian army, other armed forces, and intelligence agencies. It focuses heavily on robust security features, access control, and data protection, aiming to meet stringent government security standards. It's a compelling case study of a national security apparatus leveraging the transparency and auditability inherent in open source code, which is quite a different approach from security through obscurity, sometimes seen with proprietary systems.
Wow, Linux for national security, that's serious.
Farad Operating System Solutions. BIS Linux. This is India's own national distribution, developed by CDAC. It's promoted for adoption within government departments and also aims to foster the growth of the local Linux ecosystem in India, often with strong localization support.
India's own distro.
Cool. Kanema. Similarly, this is a Venezuelan Linux distribution based on Debian, developed and promoted primarily for government agencies and educational institutions within Venezuela as part of national technology initiatives.
Another national effort.
Coral Linux. This was a short-lived but notable attempt back in the late 90s, early 2000s. Corel, the company known for WordPerfect and CorelDRAW, created a user-friendly desktop distribution based on Debian, aiming to bring Linux to a mainstream consumer audience. It didn't last long, but it was an interesting early effort.
Corel tried Linux. Didn't know that.
Crunch Bang Linux, often written as hashtag. This gained a strong following among users who valued speed, efficiency, and minimalism. It was a lightweight distribution featuring the very lean open-box window manager instead of a full desktop environment like GNO or KDE. Great for older hardware users who preferred a less resource-intensive setup.
For the minimalists.
Dev 1. This is a significant and ongoing fork of Debian. It was started by a group of developers and users who disagreed with Debian's decision to adopt systemed as the default init system. Dev 1's primary goal is to provide users with a choice of init systems, like the traditional sysvinit or OpenRC, maintaining compatibility with Debian packages while offering that freedom. It represents a philosophical stance on system architecture for advanced users.
A fork over the init system. Interesting.
Dream Linux. A Brazilian Linux distribution that was known for its attractive X-Space-based graphical environment and a strong focus on multimedia capabilities out of the box.
From Brazil.
eLive. This distribution stands out by featuring the Enlightenment window manager as its default. Enlightenment is known for being visually distinctive, fast, and aiming for an intuitive yet powerful desktop experience. eLive builds on Debian to provide that.
Enlightenment.
Yeah.
Haven't heard of that one.
Debian Grip. This was a project focused on creating a small footprint Linux distribution, highly compatible with standard Debian, specifically designed for resource-limited embedded systems and devices where storage space and memory are tight.
Tiny Debian for embedded.
Phoenix, a very small, text-based system administration live CD. It boots quickly and is packed with tools for system recovery, network troubleshooting, disk management, and installations. Invaluable for sysadmins and available for multiple computer architectures by 86, PowerPC,
A sysadmin's rescue disk.
GNU Sense. This distribution is notable for being sponsored by the Free Software Foundation, FSF. It adheres strictly to the FSF's guidelines for free software distributions, meaning it includes only 100% free software, deliberately excluding any proprietary drivers, firmware blobs, or non-free applications, a purely ideological choice.
The purest FSF distro.
Grum LA.
Yeah.
Against Rimmel. Another live CD USB distribution like Phoenix, designed specifically for system administrators and text tool users. It's packed with command line utilities for system recovery, network analysis, and administration tasks.
Another rescue tool.
Handy Linux. This was a really nice Debian GNU Linux derivative designed with a strong human-centric approach. It was specifically tailored for computer novices, particularly seniors, often using older or slower computers. It focused on simplicity, ease of use, and accessibility features.
Linux for seniors. That's thoughtful.
Instant Web Kiosk. A specialized, lightweight, browser-only operating system. It boots directly into a web browser locked down in kiosk mode. Ideal for digital signage displays, public internet terminals in libraries or hotels, and similar single-purpose web access environments.
Turns a PC into a web kiosk.
Kali Linux. This is perhaps one of the most widely known specialized Debian derivatives today. Kali is a complete, highly customizable operating system specifically engineered and preloaded with hundreds of tools for penetration testing, digital forensics, reverse engineering, and cybersecurity vulnerability assessment. It's the go-to toolkit for cybersecurity professionals, researchers, and ethical hacking enthusiasts worldwide.
Ah, yes, Kali. The hacker's choice.
Phonetics, an installable live DVD-CD distribution based on Debian's stable branch, aimed at desktop usage. It was known for providing convenient scripts and tools to ease configuration and hardware setup.
Easier Debian desktop.
And finally, Knoppix. We have to mention Knoppix again because it was such a pioneer. Created by Klaus Knopper, it was one of the very first widely recognized and popular live CD versions of Debian GNU Linux. It allowed users to boot a full Linux desktop environment directly from the CD without installing anything to their hard drive. This revolutionized Linux accessibility and demonstrated the power of live systems back in the early 2000s.
Knoppix, the original live CD pioneer. That's an incredible list. It really showcases the immense breadth of Debian's influence and the sheer power of the open source model to allow for this level of specialization and adaptation. And Knoppix itself, that pioneer you mentioned, it spawned its own derivatives too, right? Kind of extending that live CD legacy.
Yes. Knoppix, with its groundbreaking live CD functionality and excellent hardware detection scripts, became the base for several other interesting, often lightweight and specialized distributions. Damn Small Linux, DSL. This was absolutely ingenious in its time. DSL was designed to run on incredibly old hardware, often with very limited RAM, could run reasonably in 16 MB. It packed a surprising amount of functionality into under 50 MB. Because of its incredibly low memory requirements, it became commonly used on virtual machines or as a quick booting rescue system. It really proved that powerful computing doesn't always need heavy resources.
Damn small Linux, aptly named, under 50 millib. Wow.
Feather Linux. Similar to DSL in being lightweight, Feather Linux was another Knoppix-based distribution that could boot directly from either a CD or a USB flash drive. It also utilized Knoppix's excellent hardware detection capabilities to try and get up and running quickly on a variety of machines, focusing on fitting essential desktop applications into a small footprint.
Another lightweight Knoppix child.
Hikarinix. Now, this is a perfect example of hyper-specialization. Hikarinix was a bootable Linux CD based on damn small Linux, which was based on Knoppix, specifically designed for people interested in studying and playing the ancient and complex strategy board game of Go. It included Go software, study aids, and connectivity to online Go servers. Demonstrates just how niche a distribution can become.
A Linux distro just for playing Go. That's amazing dedication. Okay, and then of course there's Ubuntu. Ubuntu has arguably done more than any other single distribution to bring Linux to a much wider mainstream audience with its consistent focus on user-friendliness, regular release cycles, and accessibility. It's probably the most famous Linux distribution for personal computing, wouldn't you say?
Indeed. Ubuntu, which is itself based on Debian, has been incredibly influential in making Linux more accessible and appealing to a mainstream audience worldwide. It acted as a gateway for millions of users who might not have otherwise tried Linux. And unsurprisingly, Ubuntu also has its own thriving ecosystem of official and community-driven derivatives, each focusing on a slightly different user need, software selection, or desktop environment.
So Ubuntu has its own family, too.
It does. For example,
this was an official derivative, though its status has varied, specifically targeted for use in primary and secondary education environments. It aimed to provide a ready-to-use platform bundling relevant educational software, classroom management tools, and integration with educational infrastructure. It's a fantastic example of Linux making a direct, positive impact in classrooms.
Linux in schools. Great.
Kubuntu. This is one of the main official Ubuntu derivatives, or flavors. It uses the KDE Plasma desktop environment instead of Ubuntu's default, which is typically GNOME. Kubuntu offers a different look and feel, a distinct set of default applications from the KDE ecosystem, and appeals to users who prefer KDE's approach to the desktop.
Ubuntu with KDE.
Lubuntu. Another popular official flavor, Lubuntu is specifically designed to be lighter, faster, and more energy efficient than standard Ubuntu. It typically uses the LXQT desktop environment, previously LXDE, which requires fewer system resources. This makes Lubuntu an excellent choice for older or less powerful hardware, netbooks, or simply for users who prefer a minimal, snappy desktop experience.
Ubuntu, but later.
And Mythbuntu. This was an interesting official derivative focused on home theater PC, HTPC enthusiasts. Based on Ubuntu, Mythbuntu provided a streamlined installation and pre-configured setup of the MythTV personal video recorder, PVR software. It was tailored for recording TV, managing media libraries, and acting as a powerful media center front-end, essentially turning a PC into a TiVo-like device using open-source software.
Ubuntu for your TV recorder. Cool niche. Hashtag outro. Wow. We have truly journeyed today, haven't we? All the way from the very genesis of the Linux kernel's birth back in '91, slicing through its core architecture, seeing its ubiquitous applications everywhere from servers to routers, and finally landing in this vast, diverse galaxy of Linux distributions out there.
It's quite a universe.
It really is. We've seen how this profound commitment to open source principles and user freedom has led to an operating system that's not only incredibly powerful, flexible, and deeply customizable, but also just astonishingly ubiquitous. It's quietly powering everything from the smallest embedded device maybe in your coffee maker, all the way up to the world's fastest supercomputers crunching massive scientific data sets.
An incredible range.
We've peeled back the layers of its unique unified file system that single root to. We've empowered ourselves, hopefully, with the precision of command line mastery understanding PWD CDL's arguments and those control operators. And we've even glimpsed the incredible automation potential that shell scripting offers, moving beyond just using Linux to making it work for you. This deep dive, I think, truly shows the remarkable depth and breadth of the Linux world.
It really is more than just software, isn't it? It's a testament to collaborative development on a global scale, the sheer power of shared knowledge when licenses permit it, and that enduring vision of digital freedom that started it all.
Absolutely. So as you go about your day, interacting with technology in countless ways, picking up your phone, browsing a website, maybe even adjusting your smart thermostat, consider this. How might understanding these principles of open source freedom, as so robustly embodied by Linux for decades now, how might that change the way you approach technology or problem solving or even collaboration in your own work or life?
It's a powerful model.
It really is. And maybe ask yourself, what surprising places might Linux be quietly hiding in your world right now, powering the infrastructure you rely on every single day without even a second thought? Perhaps it's time to pull back that curtain just a little further yourself and explore.